Okay, so now we move to the next topic, which is discussing about isomorphism of graph. We often need to know whether it is possible to draw two graphs in the same way. Okay, two graphs in the same way. That is, do the graph have the same structure? Same structure when we ignore the identities of their vertices. Again, do the graphs have the same structure when we ignore the identities of their vertices? So what does it mean? Okay, so isomorphism actually is about uh, discussing about two different graphs. Okay, two different graphs. Then we want to see whether these two graphs have the same structure or not. Okay, have the same structure or not. Alright, so let's consider the definition of isomorphism. The simple graph denoted as G1 with vertices set V1 and edges set E1, and another graph denoted as G2 with vertices set V2 and edges set V2. So the simple graph G1 and G2 are isomorphic if there exists a one-to-one and onto function. One-to-one and onto function from the set V1 to set V2. Alright, again, the simple graph G1 and G2 are said as isomorphic. Okay, isomorphic if there exists a one-to-one and onto function from the set V1 to the set V2. Alright, from the set V1, which consisting all the vertices of the graph G1, to the set V2, okay, which consisting all the vertices for the graph G2. So G1 and G2 are said to be are isomorphic if there exists a function f from V1 to V2, where the function f is required to be a one-to-one and onto function. One-to-one and onto function. Okay, with the property that A and B are adjacent in G1 if and only if FA and FB are adjacent in G2. Alright, let's say we have A and B. Okay, A and B are vertices belongs to the graph G1, and we also have FA and FB which belong to the graph G2. Alright, so the condition to be isomorphic, first we have function f that mapping from V1 to V2, where the function f is one-to-one and onto function. And the next condition is if A and B are adjacent in V1, okay, A and B are adjacent in G1, so FA and FB are required to be adjacent in G2 for all A and B and in the set V1. Such a function f is called an isomorphism. Okay, the graph G1 and G2 are said as isomorphic, so the function is referred to as isomorphism. Two simple graphs that are not isomorphic are called as non-isomorphic. Okay, I give you example. Show that the graph G and the graph H displayed in the following figure are isomorphic. Okay, so they are isomorphic. So your task is to show that, to give the evidence how we can say that these two graphs are isomorphic. So we are given two different graphs, graph G and graph H. Graph G with sets V and E and graph H with sets W and F. Okay, so isomorphic means two different graphs with the same structure. Okay, as you can see in the graph G and graph H, okay, they are almost similar. Alright, so if we check one by one vertex in G and one by one vertex at H, we can see that there are corresponding entries between the graph G and the graph H. For example, A. Okay, as you can see, A is adjacent to the vertex D. Okay, to the vertex D, where the vertex D is adjacent to only a single vertex, which is A. At the graph H, we can see that the vertex H is just like the vertex A. Okay, just like the vertex A, because it is also connected to one vertex, which is W, where the vertex W is connected only to single vertex, which is X. So there is a significant similarity between the vertex A and the vertex X. Alright, so that's why we can say that we have set V, we have set W for the graph H. So now we need one function that move from V to W in order for G and H to be isomorphic. And this function f is required to be one-to-one and onto. So in V we have A, we have B, we have C, and we have D as vertices in the set V. In the set W, which belongs to the graph H, we have X, we have W, Y, and Z as the vertices in the set W. Alright, so now we want to check whether the function f is one-to-one and onto. One-to-one and onto. Alright, so we divide G and H into two sets. Okay, where the first set is V, which is containing all the vertices for the graph G, and the second set is W, which is consisting all the vertices of the graph H. Alright, so as you can see in this figure, we say that A is just like the vertex X in the graph H. Alright, so we map from A, move to X. So in the next graph, we can see that D has the same structure or the same rule as the vertex W. It pointing to a single vertex. W also pointing to a single vertex. So we map D to W. Okay, D to W, A to X. Okay, for B, this vertex is similar or just like the vertex Y. Okay, it is connected to X and X is connected to W. So B is connected to A is connected to D. So we can map B to Y. B to Y. And finally, the remaining vertex is C. So we map C to Z. So from here we have, okay, FA equal to X, FB equal to Y, FC equal to Z, and FD equal to W. Alright, so next we check whether the function f is one-to-one and onto. Yes, it is one-to-one because one element in the V is mapped to one element in W. Okay, so the function f is one-to-one. The second question, it is onto. Onto means it covers all the elements in V. Yes, it covers all the elements in V. Okay, there is no remaining vertex. Okay, A, B, C, and D, all the vertices pointing to the corresponding entry in the set W. So we say that the function f is one-to-one and onto function from G to H. Okay. The next task is to check. Okay, to check the second condition is about the adjacency of the vertex in G and H. Alright. So we have A and B in the set G. So A and B are adjacent in G, while FA, which is X, and FB, which is Y, are adjacent in H. The next vertices are B and C. B and C are adjacent in G, while FB, which is Y, and FC, which is Z, are adjacent in H. We move to next vertices. We have CA. C and A are adjacent in G, while FC, which is equal to Z, and FA, which is equal to X, are also adjacent in X. Okay, so we move to the last vertices. We have A and D. A and D are adjacent in G, while FA, which is X, and FD, which is W, are adjacent in H. So according to the definition, we can conclude that the given graph G and H are isomorphic. Alright, determining whether two simple graphs are isomorphic. So basically, maybe in exam you'll be given two graphs, okay, and your task is to determine whether the two graphs are isomorphic or non-isomorphic. It is often difficult to determine whether two simple graphs are isomorphic. Okay, previously we're dealing with simple graph G and H. So of course it is easy to determine. Okay, it is easy to determine the whether the given graphs are isomorphic or not. But most of the cases, it is often difficult to determine the isomorphic properties of the graph. There are n factorial possible one-to-one correspondence between the vertex set of two simple graphs with n vertices. Just like in the previous example, we map from A to X. Alright, so actually there are n factorial possible one-to-one correspondence. Testing each such correspondence to see whether it preserves adjacency and non-adjacency is impractical when n is large. Means when there are so many vertices. Okay, previously we're dealing with 5 vertices only. Okay, 5 vertices. So what happens if n is large? For example, n equal to 10. So it becomes cumbersome and it becomes difficult to determine whether the given graphs are isomorphic or non-isomorphic. Sometimes it is not hard to show that two graphs are not isomorphic. Okay, so you have a second option. Instead of showing that the given graph are isomorphic, you also can go to the second alternative, which is to show that the given graph are non-isomorphic. Okay, to find evidence that the given graph are non-isomorphic is easier than to show that the given graph are isomorphic. In particular, two graphs can be shown as non-isomorphic if we can find single property, only one property. Okay, find a property only one of the two graphs has, but that is preserved by isomorphism. A property preserved by isomorphism of graph is called graph invariant. What does it mean? Graph invariant. Invariant means the value are equal. Okay, the value are same. For instance, isomorphic simple graph must have the same number of vertices. That means if we are given graph G and graph H, so if the graph G has, for example, n equal to 6, means that there are 6 vertices in the graph G. So the graph H also must has 6 vertices. Okay, If H, suppose H has 7 vertices, you can immediately conclude that G, H, and H are non-isomorphic because the number of vertices are different. Because if two graphs are isomorphic, so number of vertices is considered as invariant. That means they must have the same number of vertices, okay, in order to be considered isomorphic. All right. Isomorphic simple graph also must have the same number of edges. So other than same number of vertices, so in order to be isomorphic, the graphs also must have same number of edges. Okay, if the given graph G and H has different number of edges, okay, so automatically or immediately you can conclude that the given graphs are non-isomorphic. All right. Because the one-to-one correspondence between vertices establishes a one-to-one correspondence between edges. In addition, the degree of the vertices in isomorphic simple graphs also must be the same. So the degree also considered as graph invariant. That is, a vertex V of degree D in G must correspond to a vertex FV with the same degree D in H. So in the previous example, we have vertex A, we say as correspond to the vertex X. Okay, vertex A in the graph G, vertex X in the graph H. So when we check, the degree of the vertex A is equal to 2. Okay, so same goes with the X. The degree of the vertex X also equal to 2. Okay, we check back the example. Oh, not 2 but 3, because A is incident to B, C, and D. So X also incident to Y, W, and Z. So not 2 but 3, but still the same degree. Okay, the corresponding entries have the same degree. All right. Because a vertex W in G is adjacent to V if and only if FB and W are adjacent in H. That's the reason. Okay, another example with the same question, but this time you need to show that the given graph G and H are non-isomorphic. Okay, so to check these two graphs are non-isomorphic is easier than to show that these graphs are isomorphic. Okay, so these two graphs are non-isomorphic. So your task is to find evidence to say that these two graphs are non-isomorphic. So to give the evidence, we can use the invariant values. We check one by one the number of vertices, number of edges, the degree of each corresponding vertices. Okay, if we can find any value that different between G and H, then we can immediately conclude that G and H are non-isomorphic. Okay, let's check one by one. Solution. Let G equal to VE and HWF. Okay. Note that the cardinality of the set V means the number of vertices of G is equal to the cardinality of W, which is representing the number of vertices in H. They are same, equal to 5. Let's check. How many vertices? 1, 2, 3, 4, 5. In H, we have 1, 2, 3, 4, 5. Okay, so that means both graphs have the same number of vertices. So how about H? So we have set of H E, set of H F. Okay, let's check how many edges. So in G we have 1, 2, 3, 4, 5, 6 edges. So in H we have 1, 2, 3, 4, 5, and 6. Okay, so the number of edges also equal. So the two graphs pass these two tests, but not necessarily the graph is isomorphic. We still need to check other invariant value. So the next value is the degree of each vertex. Okay, in both graph, each vertex has the following degree. Degree for the vertex A equal to 2. Okay, in A, it is corresponding to A. So the degree, wait. Alright, so the next value to be checked is the degree. The degree of the corresponding vertex. Corresponding vertex in the graph G and corresponding vertex in the graph H. So as we can see, in the graph G we have vertex E. Vertex E with degree 3 because it is incident to 3, adjacent to 3 vertices. It is adjacent to A, C, and D. So the degree of E equal to 3. In the graph H, we also have vertex with such property. We have A. A also has 1, 2, 3. Okay, so in the graph H, we have vertex C with role almost similar with the vertex E because vertex C also has degree equal to 3. Okay, so maybe we can map from E to C. Next is C. So C in the graph G has 1, 2, 3. So the degree is equal to 3. But in the graph H, we cannot find any other vertex with degree 3 because for D the degree equal to 2, B the degree equal to 2, E the degree equal to 1, and A equal to 4. There is no other vertex in H with degree 3. That means we cannot map C to any other entry to the graph H. So then we can say that these two graphs are not isomorphic. Okay, because we cannot find any pair for C. For E, yes, we can say that it is, we can map to C. E, we can map to C. But for C, we cannot map to any other vertices in the graph H because of the difference in degree. Alright, where in the definition, degree of corresponding vertices are considered as invariant. Mesti sama. Okay, equal value. If we map C to D, so their degree must invariant or equal. But this time, degree 3, we cannot map to any other vertex because only single entry in H has degree equal to 3. Then we can conclude that the given graph are non-isomorphic. Alright, so the number of vertices, the number of edges, and the number of vertices of each degree are all invariant under isomorphism. So when your task is to check whether the graph are not isomorphic, so better you check one by one these values. The number of vertices, make sure they are equal. Number of edges also make sure they are equal, and also the number of vertices of each degree also are equal. If one of these values are different, so we can say that the given graph are not non-isomorphic. If any of these quantities differ into simple graphs, so these graphs cannot be isomorphic. However, when these invariants are the same, it does not necessarily means that the two graphs are isomorphic. So, although the given graph can pass all these tests, all these values, means the number of vertices are equal, the number of edges also equal, the number of vertices of each degree also equal, we still cannot say that the given graph are isomorphic. Okay, they are not necessarily isomorphic, not yet, because again we need to check back the definition to be isomorphic. There are no fixed sets of invariant currently known that can be used to determine whether simple graphs are isomorphic or not. Alright, so next example, determine whether the graphs shown in the following figure are isomorphic or not. Okay, in the previous two examples, the given graph are isomorphic and non-isomorphic. So your task is to provide the evidence. In this example, your task is to determine whether the given graph are isomorphic or non-isomorphic. Alright, so the graph G and H both have 8 vertices. So first we check the number of vertices. Yes, the graph G has 8 vertices. So same goes with the graph H. Graph H also has 8 vertices. The graph G has 10 edges. The graph H also has 10 edges. So they pass these two tests. Alright, number of vertices and number of edges. Next, they also both have 4 vertices of degree 2 and 4 vertices of degree 3. Okay, same number of vertices with degree 2 and same number of vertices with degree 3. That means it is possible for us to map from the graph G to graph H. Because these invariants all agree, it is still conceivable that these graphs are isomorphic. So not yet, we cannot conclude these two graphs are isomorphic, not yet. Okay, next, since degree A equal to 2 in G, then A must correspond to either T, U, X or Y in the graph H, because these vertices are the vertices with degree 2 in the graph H. Means A is corresponding either to T or maybe U or maybe X or maybe Y, because all these vertices has degree 2. Not that the vertex A is adjacent to B, where degree of B equal to 3, and A also adjacent to D, where degree D equal to 3. Alright, let's check the graph. Vertex A. Okay, the vertex A is adjacent to D. Let's check the degree of D. Degree of D is equal to 1, 2, 3. Degree of D equal to 3. And then A also adjacent with B. So degree of B is 3. 1, 2, 3. Okay. On the other hand, so when we check the graph H, okay, at the graph H, the vertex T is adjacent to S, where the degree S is 3. And the vertex T also adjacent to U, where the degree of U is 2. So if we say that A is corresponding to T, so T also must adjacent to 2 vertices with degree 3 and 3. But then T is adjacent to vertex S with degree 3, but the degree of U, which is another vertex adjacent to T, is degree 2. Okay, it must equal to 3 and 3. Then we can say that A is corresponding to T. So because the degree of U equal to 2, so we can say that T is not corresponding to A. So we cancel this one. Next is U. The second candidate is U, because we have T, U, X, and Y. So we check one by one. So for U, U is adjacent to T, where the degree of T equal to 2. And U also adjacent to V, where the degree of V is equal to 3. For V, it is okay, because the degree is equal to 3. But T, the degree is 2. Whereas we need that both the degree of both vertices correspond to A are equal to 3. But for u, one of the vertex is with degree 2. So immediately we can eliminate u as the candidate to be corresponding with A. The next candidate is X. So X in the graph H is adjacent to W, where degree of W equal to 3. This is one is okay. But it is also adjacent to V, where the degree, not V, it's Y. Okay. Degree of Y equal to 2. Okay, whereas in order to be corresponding with A, we need both degree equal to 3. But because this one is 2, so immediately we can cancel X. So the final candidate to be corresponding with A is Y. So check in the graph H, Y is adjacent to X, where the degree of X is equal to 2, and Y is also adjacent to Z, where the degree of Z is equal to 3. This one okay, but this one not okay. Okay, because in order to be corresponding with A, we want both degree for the vertices must equal to 3. So also we can cancel Y. So the conclusion, there is no vertex among T, U, X or Y that is adjacent to vertices with degree T. Okay, with degree 3 as happened with the vertex A. That means there is no vertex in the graph H that can be corresponding with A. So A in the graph G, okay, A cannot be mapped to any other vertex in the graph H. There is no vertex in graph H that can be mapped with A. So our conclusion is, therefore G and H are not isomorphic. Alright. We move to the connectivity. Many problems can be modeled with path. Okay, with path formed by traveling along the edges of graph. Okay, so path is means laluan. Okay, the jalan lah. Okay, laluan. For instance, problems of efficiently planning routes for mail delivery, garbage pickup, diagnostic of computer networks, and so on can be solved using models that involve path in graphs. So there are a lot of application of path in graphs. Informally, a path is a sequence of edges. Okay, a sequence of edges means we have several edges we form in sequence. Okay, for example, we start with E1, move to E2, move to E3, okay, and so on. So there is a sequence of edges in the path that begins at a vertex of a graph and travels from one vertex to another vertex along edges of the graph. Alright, so a path is a sequence of edges. So when it is a sequence means the order is matter lah. Which one is come first, second, and so on. So this is the proper definition for the path. For natural number n, okay, let n be a natural number and G be an undirected graph. A path of length n. A path of length n from U to V. Okay, from one vertex U to another vertex V, okay, move from U to V, okay, the length is n, is a sequence of n edges. That's why the length is n. Okay, a sequence of n edges denoted as E1, E2 up to En of the graph G, for which there exists a sequence x0 which is equal to U, x1 up to xn minus 1 up to xn which is equal to V of vertices such that EI has the endpoints xi minus 1 and xi for all I equal to 1 up to n. Alright, so we have x0 equal to the starting point U, and it is ended with xn which is the terminal point V, because we're moving from U to V. Okay, we want to see the path. How many edges involved in order to reach U, in order to reach V from U. When the graph is simple, denote this path by its vertex sequence x0, x1 up to xn, because listing these vertices uniquely determines the path. The path is a circuit. Okay. What is the condition? If it begins and ends at the same vertex, that means it starts from you, okay, a have of path, and finally back to you. Okay, so this kind of path is said as circuit. It begins and ends at the same vertex. Okay, that is u equal to v, and has length greater than 0. That means it moves, but finally it backs to the same vertex. Then we said that kind of path as circuit. The path or circuit that is said to pass through the vertices. It passed through the vertices x1, x2 up to xn minus 1, and also said as traverse the edges e1 up to en. A path or circuit is simple if it does not contain the same edge more than once. Okay, that means it passes through edge only one time, only once. Okay, it does not contain the same edge more than once. Okay, I give you example. Consider the following simple graph. Alright, so what is the question? Okay, from the given graph, we have the following information. The graph shows that A, D, C, F, and E is a simple path of length 4. Okay, because we have A to D, D to C, A to D, D to C, C to F, and F to E. Alright, so A, B, C, D, F, E means the path is moved from A to D, and then from D it moves to C, from C it moves to F, and from F it moves to E. So that is the path, okay, from A to E, and all edges are different edge. There is no same edge appears, so that's why we call it a simple path. Every edge appears only once. Okay, only once. So we have this one we consider as E1, E2, E3, and E4. So that's why the length of this path is 4. Okay, the second information, DECA is not a path. Why? Because EC is not an edge. Okay, so DECA means we move from D to E, from E we move to C, from C we move to A. But then we refer back to the given graph. Okay, E and C are not connected. There is no way we can move directly from E to C. There is no edge connecting E and C. So that's why we say DECA is not a path, because EC is not an edge. There is no edge connecting E and C. Alright, so BCFEB, it starts with B and end with B. So this path is a circuit of length 4, because BC, CF, FE, and EB are edges, are all edges. How many edges? 4 edges. So that's why the length is 4. Right? So this path is called circuit because it starts with B and ended also with B. Alright, that's why we call it as circuit. The path ABEDAB, which is of length 5, is not simple. It is not simple. Why? Because it contains the edges A and B appear twice. Okay, so that's why this path is considered as not simple path. Next is connectedness in undirected graph. Connectedness in undirected graph. So definition, an undirected graph is called connected if there is a path. There is a path between every pair of distinct vertices of the graph. Again, an undirected graph is called connected if there is a path between every pair of distinct vertices of the graph. An undirected graph that is not connected is called disconnected graph. We say that we disconnect a graph when we remove, okay, when we remove vertices or we remove edges or both vertices and edges to produce a disconnected graph. So we said that we disconnect a graph. Any two computers in the network can communicate if and only if the graph of this network is connected. So that's the application. Okay, consider the following graph. I give you two different graphs, G1 and G2. The graph G1 is connected. Why? Because for every pair of distinct vertices, there is a path between them. Okay, let's say we want to move from G to E, so of course there is a path from G to E. Let's say we want to move from E to A, so we have a path from E, move, okay, from E, move, edit like this. Also we can go this way, also can. Okay, so every distinct vertices are connected. In the graph G1. We can make path, okay, from one vertex to another vertex. All right, so how about G2? So clearly, okay, there are some disconnected points. For example, D and C, they are not connected. We cannot move from F to A because, okay, there are disconnected vertices here. So the graph G2 is said as not connected. Theorem. There is a simple path between every pair. There is a simple path between every pair of distinct vertices of a connected undirected graph. A connected component of a graph G is a connected subgraph. Okay, means G is the main graph. So connected components is a connected subgraph of the graph G that is not a proper subgraph of another connected subgraph of G. That is, a connected component of a graph G is a maximal connected subgraph of G. Okay, I know it's quite complicated to understand about the connected component, but don't worry, I will give you example. A graph G that is not connected, okay, a graph G that is not connected has two or more connected components that are disjoint and have G as their union. Okay, means that means there are more than two or more connected components, and these connected components are disjoint. There is no common vertex or common edge in these components. When we combine these components together, we can get the original graph G as their union. So this is the example. What are the connected components of the graph H as shown in the following figure? Okay, the whole graph, okay, from this one, and this one, when we combine together, we have single graph H. But this graph is disconnected, right? So, however, we have connected components of this graph. The graph H is the union of three disjoint connected subgraph H1, H2, and H3. Okay, so H1, H2, and H3 are connected components of the graph H because there are three subgraphs and these three subgraphs are disjoint from each other. Okay, there is no common vertex in H1, in H2, and H3. But when we combine together all these three subgraphs, that means we union H1 union H2 union H3, so the outcome is the whole graph H. Alright, so that's why we call these three subgraphs H1, H2, and H3 as connected components of the graph H. Connectedness in directed graph. So previously in undirected graph. So this one is this time the connectedness in directed graph. Okay. A directed graph is strongly connected. Strongly connected if there is a path from A to B and from B to A. Okay, there is a path, not edges but path, means sequence of edges, combination of edges from A to B and from B to A. So we can say that the graph is strongly connected. Okay, whenever A and B are vertices in the graph. A directed graph is said as weakly connected, previously strongly but this time weakly, if there is a path between every two vertices in the underlying undirected graph. In the underlying directed graph. There is, what is underlying directed graph? A directed graph is weakly connected if and only if there is always a path between two vertices when the direction of the edges are disregarded. Okay, that means in the directed graph we omit the direction, so we call that as underlying undirected graph. Alright, so that's the condition to be strongly connected and weakly connected. Okay, let's see the example. Yes, example. Alright. Before that, clearly any strongly connected directed graph is also weakly connected. However, a not strongly connected directed graph is not necessarily a weakly connected graph. Let's see the example. Of the directed graphs G and H shown in the following figure are strongly connected. Okay? Or weakly connected. So in order to answer this question, we need to understand the definition to be strongly and weakly connected. Alright? So we're given a directed graph G and H. So in the graph G, as we can say, there is always a path. There is always a path from one vertex to another vertex. Okay? Okay, there is always a path between two vertices in the directed graph. Let's say I want to go from A to D. So there is a path A to D. Okay, and there is also a path back from D to A. D goes back to A. Alright, so all vertices we can have a path from one vertex to the vertex, and we can going back from the vertex back to the original vertex. So that's why G is strongly connected, because there is a path between any two vertices in the directed graph. So automatically G is also weakly connected graph. When it is strongly connected, it is also automatically said as weakly connected. Alright, so how about the graph H? The graph H is not strongly connected. Okay, not strongly connected. There is no directed path from A to B in this graph. Okay. From B to A, yes, there is a path here. B to A, easy. But back from A to B, there is no path. Okay, there is no path from A to B because the direction of this H is to A. The direction of this H also moves to A. So there is no way from A to B. There is a way from B to A, but there is no way from A to B. So we can say that the graph H is weakly connected. Alright? Because there is a path between any two vertices in the underlying undirected graph of H. Alright. Counting path between vertices. How many paths that we can form between vertices? Theorem. Let G be a graph with adjacency matrix A. Still remember about the adjacency matrix? Okay. Let G be a graph with adjacency matrix A with respect to the ordering V1, V2 up to Vn of the vertices of the graph. For natural number R, so the number of different paths of length R from Vi to Vj equals to the ijth entry of the a to the power of r matrix. Okay, so the number of different paths at each path with length r. Okay, from Vi to Vj. So we have I here and j here. Okay, so the number of the path equals to the ijth entry. The value for the entry at the location row number I and column number j at the a to the power of r matrix. Okay, so A is the original adjacency matrix. So what we check is the A to the power of R. That means we need to multiply the matrix A R times. A times A times A. How many times? R times. Okay, so the entry at this location, ij location, is representing the number of different paths of length R from Vi to Vj. Okay, I give you example. How many paths? Okay, we are interested on the number of paths of length 4. Automatically, we know that R equal to 4. Are there from A to D? From A to D. In the following simple graph. Alright, in the following simple graph. Okay, let's have the answer, how to answer this question. This is the solution. We know that the given R equal to 4 because the length is equal to 4. The adjacency matrix of G with ordering vertices A, B, C, D is given in the matrix A. Okay, so we have A, B, C, D because that is the given order. A, B, C, D. Alright, as we can see in the graph, there is no loop at A, so the value is equal to 0. A and B are connected. A and B are connected, so we have 1 here. A and C also connected. Okay, so we have 1 here. A and D are not connected. Okay, A and D are not connected here. So the value is equal to 0. So we'll continue the same process until we cover all the entries of the adjacency matrix of G. Alright. So in order to compute the number of paths with length 4, okay, length 4 from A to D. That means in this arrangement, we know that A is V1, the first vertex, while D is V4, which is the fourth vertex. So from that, we know that I equal to 1, J equal to 4. Alright, so the number of paths of length 4 from A to D is at the position 1, 4. Because I equal to 1, J equal to 4. Entry of A 4. When we multiply this matrix A 4 times, A times A times A times A, so the outcomes is A to the power of 4, where 4 is R. So the matrix yield by this multiplication is this, 8008 and so on. So we check the I4 position, means row number 1, column number 4. So this is the answer. Okay, this is the answer. So there are exactly 8 different paths of length 4 if we move from A to D. That is the answer. Okay, so we can list down all the paths. Okay, as we can see here, there are exactly 8 different paths. Okay, to move from A to D. From A to D, there are 8 different paths with length 4. All the paths with same length. Okay, A to B, 1. B to A, another 1. A to B, 1. B to D, 1. So total, there are 4 edges. Okay, means the length of the path is 4. Alright. Shortest path problems. Many problems can be modeled using graph with weights assigned to their edges. At the edge, we can assign numbers, and these numbers are referred to as weights. As an illustration, consider how an align system can be modeled. We set up the basic graph model by representing cities by vertices and flights by edges. Okay, from this model, okay, we can arise some problems. For example, the problem involving distances can be modeled by assigning distance between cities to the edges. Okay, other than that, flight time also can be modeled by assigning flight time to the edges. And fares can be modeled by assigning fares to the edges. So all the assigned value to the edges are in the form of numbers. Distance can be represented in numbers. For example, 1,000 kilometer. 1,000 kilometer is a number. Assigning flight times, for example, 0830, okay, means 8:30 a.m. So this one also in number. Assigning fare, for example, how many dollar? A ringgit. RM 500. So 500 is a number. So we can assign numbers to the edges. So all these numbers are referred to as weights. Okay, this is the example of the model. Okay, the cities and the vertices and the edges we can represent time. Okay, time at the edge we can represent time. At the edge also we can represent the mileage. At the edge also we can represent the fares. So all these representations are in numbers. Okay, graph that have number assigned to each edge are called weighted graph. Weighted graph. What is a shortest path? Shortest path, that is a path of least length between two given vertices. Okay, maybe you curious why and not the. Why a shortest path, not the shortest path? Because maybe it could exist more than one path with the same value, and the value is the smallest among all value of path. Okay, maybe we can have more than one path with the least length. That's why we have a instead of the. Alright. In the align system presented by the weighted graph, so we can arise several questions. First, what is the shortest path in the A distance between Boston and Los Angeles? Means, what is the shortest path? Means the least or the smallest number of kilometer, okay, from Boston to Los Angeles. Is there a path with the smallest number of kilometers? So that is the question. The second one, what combinations of flight has the smallest total flight time? Okay, flight time, that is total time in the air not including time between flights between Boston and Los Angeles. Okay, if you rephrase the question, macam mana kita nak paling cepat daripada Boston ke Los Angeles? The smallest total flight time. And the third question, what is the cheapest fare between these two cities? Okay, so we also can answer this question using graphs, the model graphs. Alright. Another important problem involving weighted graph asks for a circuit of shortest total length. Okay, what is circuit? Started at same point and ended also at the same point. Start from you and ended at you. We call it as circuit. Okay, of shortest total length that visits every vertex of a complete graph exactly once. So this is the famous traveling salesperson problem. Okay, famous traveling salesperson problem, which asks for an order in which a salesperson should visit each of the cities on his route exactly once, so that he travels the minimum total distance. So actually this is one of the real life problems. Okay, one real life problems existing in courier services. Okay, courier services, for example, nowadays we're using Shopee, Lazada, and so on. So for the courier services, of course, the courier company wants to minimize the cost. So to minimize the cost means the company want to find the shortest path to deliver all the items, right? So that is the example of real life application of this problem. Okay, I'll give you another example. What is the length of the shortest path between A and Z in the following weighted graph? Okay, in other words, find the shortest path from A to Z. Okay, so how to answer this question? Because this is a simple graph, so we can list down all the possible paths from A to Z. Alright, so from A to Z, we have A to D, D to E, and E to Z. A to D, D to E, and E to Z. So what is the length? 2 plus 3 plus 1. Okay, so the answer is equal to 6. Another possible way is move from A to B, B to C, C to Z. So we have 4 times 3 is 7, 7 times 2 is equal to 9. So that means the one still shorter than 9. Another possible way is A to B, B to E, and E to Z. So what is the length? 4 times 3, 7 times 1 is equal to 8. So among three possible paths, the shortest path is ADEZ. Okay, this is path ADEZ. The length of the shortest path is equal to 6. Alright, so we know that the shortest path from A to Z is A to D, D to E, E to Z, because it has the smallest value, which is equal to 6. Alright, so I think I cover all the topics in this chapter. So we finish with this chapter number 7, which is chapter about graph. Okay, thank you, class.